Good afternoon. My name is Michal Lukomski, and today I'm going to talk about sustainable approaches to preservation of museum collections. The work is done within the Managing Collection Environments, which is the research and training program of the Getty Conservation Institute. By sustainable strategy, we understand safe and affordable control and management of the temperature and humidity in the museum institutions. And this task is really complex because museums are driven by conflicting priorities. On the one side, museums should provide access to the collection, preserve this collection, and do all these things within available resources. And one can understand, of course, that every institution is different, and the level of access depends on the general aim of the museum and its mission, and also the preservation depends on the type of the collection. And therefore, we believe that there is nothing like a universal ideal strategy for the museums. The sustainable strategy for the preservation of collection and for the managing of a environment needs to be tailored and defined for each individual institution. Therefore, within the Managing Collection Environments initiative, we are looking for evidence-based processes and tools which can empower those who make the decision about the managing collections. And in our opinion, it requires rethinking collection care from a variety of angles. We would like to look at interconnected research, policy, and practice of individual institutions. Development of environmental strategy is always a process, and it doesn't matter whether it is done for the new museum or it's just improvement of existing one. It always requires planning, designing, and implementing phase, and it should be done in a very collaborative way. If done properly, this process can result in the huge potential for reducing energy consumption, can help to focus on sustainability and not only on sustainability in a financial way, can result in great flexibility in control of and operation of the museum, and very importantly, can help to integrate operation between the different departments within the museum. When working on revision of ASHRAE chapter on museum galleries, archives, and libraries, we propose such scheme of environmental strategy development. It is divided into three phases. One based on context, pre-design and design and implementation. Within this phase, focused on the context, we were looking at three particular types of information. The mission and strategy of the museum. We tried to determine needs of the collection and the building, and also understand the current environment in the museum. We also focused on the expected participation level of stakeholders. This participation level is defined for each step and each process because the role and involvement of each specialist is changing during implementation of the project. But there is also one more thing we should not forget about. The process of developing environmental strategy should be very pragmatic, should be based on risk management principles, should utilize existing research on the environmental response of the collections, and also use the shared museum experience, the experience that many collections were well maintained even in non-ideal conditions. Rethinking climate control strategy based on experience of the museum institutions should be theoretically very straightforward task. It is because observation and recording of the damage is a day-to-day operation of the museum institutions. And yet, the obtaining unbiased evidence of climate-induced change in the collection is really difficult thing, especially if we think about mechanical and physical damage. And there is many reasons for that. I will just mention few. First of all, the response of materials to climate variations is slow. It is due to the limited speed of the diffusion of the water into the material. The damage we observe is cumulative rather than catastrophic, which means it is slow and it is initially very difficult to find the correlation between the damage and improper conditions. If we add to that lack of consistent protocols for recording damage, we result in the huge subjectivity. And typically what we observe is that when damage happens, it is recorded, but when damage is not happening, even in very unstable conditions, it's very rarely collected as evidence. Therefore, it is so important for us to quantitatively characterize conditions in which damage can happen to the objects. And especially, I'm talking here about the physical or mechanical damage. So we understand very well why the damage happens. So hygroscopic objects are changing their dimensions when exposed to variations of relative humidity, and therefore different part of objects responds differently. As a result, the stresses and strains develops, and by measuring mechanical properties of a material, and especially their dimensional response to variations in climatic conditions, we can find those stresses and strains leading to deformation and cracking. The problem in our case is the size of available samples. The mechanical testing is destructive, and we cannot afford to damage precious historic samples in the big quantity. Therefore, we need to look for the methods which can help to measure mechanical properties in a very small scale. To address problem of small size of available samples, we decide to look into the micro and nano indentation technique for material characterization. The method itself is pretty simple. The principle of operation is very similar to operation of atomic force microscope. We are using a small probe or well-defined geometry to push it into the materials, and during the experiment we are measuring applied force and resulting deformation of the materials. More than that, we can also superimpose variation of the force during the indentation process, so we can measure both static and mechanical and dynamic mechanical properties of the material. And such a relation between applied force and the depth is the fingerprint of the materials, and from analysis of this curve we can measure such quantities as elastic modulus, elastic plastic energy ratio, and creep and hardness. And also, if we add this dynamic indentation, dynamic force variations, we can look at the storage and loss modulus in this dynamic mode. What is very important is the size of the imprints we are making on the material. And on this picture in the bottom right side of my slide, you can see the atomic force microscope image of the indent made by nano indentation process, and you see that the depth of the indent in this case is at the level of half of the micrometer, which means that method is virtually non-destructive. The small scale of nano and micro indentation allow us for characterization of very small objects in virtually non-destructive way. And particularly the method can be used for the historic samples in the form of cross-sections, which are routinely taken by conservators during the work with the objects. And maybe for the very first time with this technique, we can characterize the aging factors that alter the properties of paints over time, and also look at the distribution of properties across the collection of a certain age and region if we've got access to samples taken from the objects from different collections. Despite some complication with correlating mechanical properties measured in different scales, we found that properties of historic paints measured by nanoindentations are very sensitive to alternation induced by treatment or exposure to any environmental conditions. Therefore, obtained data can be used in models predicting climate-induced damage for art objects. There are, however, limitations of mechanical characterization of samples, even in very small scale. As an example, I would like to show you results obtained for distemper paint from Eidsborg Stave Church, the measurements we did within the frame of the symbol project. And in this case, you can see the sample, and on the bottom right side, the histogram showing nanoindentation results, namely the reduced storage modulus measured at the different locations. And you see that the results obtained range from 5 to 21 gigapascal. This huge range results from the fact that results of nanoindentation strongly depend on the place when we do the measurements. So it can be done very close to the void, air bubble, crack, or the particle. So generally, mechanical characterization of those highly pigmented granular and porous materials is not going to predict its behavior. It is because those defects, air bubbles, voids, and cracks, are the places when stresses concentrates and at which fracture processes can initiate. And this means that the behavior of materials is governed by the structural properties rather than the mechanical properties of the material itself. Mechanical characterization of materials has limitations for particular class of materials. Therefore, in this project, we decide to supplement the study of mechanical properties with analyzing climate-induced damage for museum collections. For this type of experiments, we selected 14 objects of different size, shape, and preservation state, and we exposed them to variations of climatic conditions. On the left side of this slide, you see the graph, which shows the change of humidity during the experiment, and you see a consecutive cycle with progressing decreasing of humidity. During the test, we were monitoring the change of the objects, trying to establish correlation between the conditions and the damage for the objects. Three techniques were used for monitoring damage progress in this experiment. Time-lapse photography focused on the accessing surface cracks, 3D imaging for looking at the warping of the object, and also acoustic emission, which monitors brittle cracking inside the material. The choice of monitoring techniques was not accidental. We selected photography, 3D scanning, and acoustic emission because they are sensitive to different damage phenomena. So on this picture, on the slide, you can see how we believe those techniques address deformation, surface phenomena, which means surface cracking and discoloration, and also the brittle cracking, which can happen during the exposure to unstable environmental conditions. Acoustic emission method was particularly important in our monitoring design. I'm not going here to present principles of the technique itself because you can see that in the other presentations during this conference. However, I would like just to mention that acoustic emission provide us the continuous measurements of a brittle cracking of the volume of the material with extremely high sensitivity, and therefore it can work as an early warning system for implementation of any climate control strategy. And we believe it's so important that we even create some guidelines on using acoustic emission in the cultural heritage field, and you can download it freely from the GCI webpage. Experiments and monitorings performed within our study show that it's very unlikely for historic objects to be damaged due to improper conditions as long as humidity does not drop below 30%. One should not, however, jump into the too fast conclusions. To establish correlation between environmental conditions and damage, we should have a very systematic approach to gathering data and also looking for the situation as a whole. Not single studies, not single objects, and it is important for both monitoring of the collection, but also for measuring properties of the materials. Obtained scientific results should always be understood and applied in context, and therefore our initiative is so much focusing on training and education. Within few last years, we created the long course, which we called Preserving Collections in the Age of Sustainability, and this is focused on mid-career professionals, those who are going to make decisions in the future museums. And the course itself focuses on decision-making process, when and how to use information, and networking, so increasing the impact of evidence-based decision. We believe that any scientific information should be used as a tool, and therefore we developed many different tools which can help conservators and practitioners to look at the situation in the museum and use them in the most effective way. And I'm not going to talk about that, but in the next talk, my colleague Vincent Beltran will describe more in details our activities related with creating tools for conservation practitioners. And I would like to conclude my talk with expressing belief that synchronized shift in policy, research, and practice can make sustainable approach for climate control strategies more available for us. What it really requires also is a collaboration between the museum institutions and research groups, and a lot of openness and honesty. At this stage, I would like to express my gratitude to Managing Collection Environment Initiative as well as the Symbol project for the supporting this research. Thank you very much for your attention.